Good morning, good afternoon, good evening to all the participants and the students for this course titled Multi-Criteria Decision Making, which is under the NPTEL MOOC series. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you know, we will be starting and finishing today the 18th lecture out of this 60 lecture series, which is spread over 12 weeks with each week being 5 lectures, each lecture being for half an hour. And the broader topic which we are still under with is basically definitions, concepts of utility theory, safety first principle and stochastic dominance. In the last class, we did start with the safety first principle and I did explain the concepts using the diagrams. We will continue that. The example which we left, go into stochastic dominance as time permits and then also the hyperbolic absolute risk aversion. Again I am mentioning whatever the coverages being mentioned in the slides, they are updated accordingly and you can refer them. So, considering the example which I drew in details for the normal distribution, the same one, if returns are normal distributed and we want to find out the minimization of the return or the decision being less than equal to RL, which RL is the minimum point or risk free interest rate. And for 3 decisions which are given as A, B and C, the corresponding values of RP bar, sigma and difference being 5% away are given in the second column, which I highlight first, the third column and the fourth column, and the diagram I have drawn in detail. So, if you see here, this is what I was hinting at. So, sorry for the repetition, but it will make things much easier for all of us to understand. So, we have B, the distribution which is marked in blue, the R bar B is given on the x axis, similarly green is for decision A, R bar A is marked, bar values being for the mean for both the cases, and sigma values with suffix B and A are denoted to signify the standard deviation, and plus minus 2 sigma means plus sigma onto the right, plus sigma onto the left. And if I convert into the concept of standard normal, plus minus 1 sigma, plus 2 sigma and minus 2 sigma, in the sense I mean the total width is 2. So, plus 1 to the right, plus 1 to the left. So, if I consider the standard normal, I would be covering about 67%, and these things are known to all of us. So, if it was 4 sigma total width, which is plus 2 sigma onto the right, minus 2 sigma onto the left. So, the total coverage would be about 97. And if I go into the concept of 6 sigma, the total width being 6 standard deviation, which is plus 3 sigma onto the right, minus 3 sigma onto the left, the total coverage area would be 99.97%. And given RL, which is onto the left, I want to find out as based on the fact the minimum area. So, if I use the green one, so I want to minimize the area here, which I am again drawing. Based on the first principle, which was minimization RP less than equal to RL. Now, if I consider the case of the green one, so this would be this area. Again the second concept, the first principle being applied for the second distribution, which is A. Now, if I consider the other two principles, I will use a different color for the safety first principles to be written down. It was minimization max of RL, and the third one was max of RP bar. So, RP bar for both the cases if I denote, and max of RL if I denote. For the max case, what will happen is this RL will be shifted onto the right, the distributions being same, which means the areas would be calculated accordingly. If I go to the max of RP bar for these two distributions, for A it will be shifted, similarly for B it will be shifted. RL remains there. So, there is no change in the RL for the third principle. In order to determine how many standard deviations RL lies below the mean, we calculate RL minus the means return divided by the standard deviation. We are normalizing it. Normalizing it in the sense that mean can be different, standard deviation can be different. So, you want to find out the excess of the average return divided by the standard deviation, or the difference in the negative side of RL and RP bar divided by standard deviation. That means, we are trying to find out so called efficiency, because if standard deviation is very high or low, so it should also come into the picture. Thus, we have to minimize the value as given here. RL minus R P bar by sigma p. This is the same thing which we have considered when we are trying to find out the minimization of RL less than equal to RP being less than equal to RL, the standard deviation concepts. So, if I minimize a function and or try to maximize the negative of the function, idea is same. So, we basically maximize RP bar minus RL, standard deviation being positive, it will continue. This is exactly equal to the concept of maximizing RP minus RF, because RL is now being replaced by RF by standard deviation, and we solve the problems accordingly. Even though for our example, we have simplified our assumption by considering only the normal distribution, which I did mention, but this would hold true for any distributions having the first and the second moments, because first moment being mean, second moment being standard deviation, and if the second moment does not exist, you cannot utilize this principle accordingly. Further extending it, according to Chebyshev's inequality for any random variable such that the expected value and variance exist, first moment and second moment exist, the following are the same. So, in the concept of Chebyshev's inequality, diagrammatically what it is. So, if I consider the line random variables, and this is basically expected value, which is Ex, and random variable x is any side, onto the left or the right. So, what I want to find out is the deviation being bound between a limit. So, for x being less, it is onto the left hand side, for x being more, it is onto the right hand side. So, I want to find out a bound for fluctuations and divide by standard deviation, because that will normalize. So, that being greater than some constant t, according to Chebyshev's inequality, the probability of that would be always less than equal to 1 by t square. Now, in case if I replace x by RP, random variable, expected value Ex by RP bar, which is obvious, and square root of variance, which is standard deviation for random variable x, would be replaced by sigma p. So, x is replaced and the random variable is now RP, and its corresponding mean and standard deviation have come. So, if this is greater than some k, it will always be less than equal to 1 by k square according to Chebyshev's inequality. Now, consider how can k be calculated. As we are interested in the lower limit, hence we simplify it as follows. So, if we are interested in the lower limit, so what if I draw the distribution, again the normal case, this is the distribution normal and this is the average value, which I denote by R p bar, R p is the random variable, and consider R L is given. So, I am trying to find out the probability onto the right hand side. So, if I denote it in green color, this is the area I want to find out. In the previous case, it was trying to find out the left hand side. So, I wanted to minimize. Here I want to basically do it and then try to maximize. Minimizing means it will push on to the left the RL line. In the same way, if I want to maximize the right hand side, it is same thing. If I move RL to the left, minimizing on the left is exactly equal to the maximizing on the right. Right part is the green one, and for convenience, I am writing the minimization using the, say for example, violet color, because the area is 1. So, minimizing 1 will maximize or vice versa. So, continuing the discussion, and if I want it to be less than some alpha, probability of being greater R p. So, in this case I just use the standard normal deviate concept, R p minus R p bar divided by standard deviation, I convert into R L minus R p bar by standard deviation, which is in the third bullet point, which I am putting a tick mark, the parts in the bracket, inside the bracket, the left hand term which is on the left hand side of the greater than sign is capital Z, and the part which is on the right hand side of the greater than side in the small z, standard normal deviate. So, if this is equal to alpha, then according to Chebyshev's inequality, if I want to draw a simile, this value can be considered as k, and if I want to basically find out the 1-to-1 correspondence, the k square value becomes this, because greater than some constant k or t. So, given standard deviation known, given R L known, given R p bar known, I can find out the bound or the maximum value or the minimum value in whichever way you are looking, because the overall sum is 1 for the probability. So, less than equal to this bound means that it cannot cross of the probability. So, even though I have been switching between and discussing all the 3 norms of the safety first principle, so yet I would like to take your time in trying to discuss the second criteria and then the third. The second criteria was maximization of RL. Maximization of RL means that if I only consider the distribution, this is R p bar, this was R L, and I want to find out R L and push it onto the left hand side, onto the right hand side. And consider I am putting a constraint now. The constraint I will put a different color is probability of R p being less than equal to R L. So, I will try pushing R L onto the right hand side, but at the same time try to basically bound the probability that R L is greater than R p or R p is less than R L with a value of alpha. And let us consider we have a value of alpha as 0.05. Then we should have, if I consider the such that conditions, again it can be converted into a standard normal. So, is R p minus R p bar divided by sigma p, which is capital Z, is less than R L minus R p bar by a sigma p, which is small z, is equal to less than equal alpha, and alpha is 0.05. So, how would we solve it? So, this is the case. We have R p bar given, the green vertical line distribution is given for R p for the decision B. So, this is R p comma B for decision B, this is the average value, and considering this, what we want to assume, if you superimpose the condition of trying to maximize subject to conditions, we are trying to basically consider R L and push it onto the right. This is what we are trying to do. Now, this implies is what? If I consider this equation, which I will put a violet tick mark. So, this would mean that if I convert that value of alpha, which is 0.05, into how many standard deviation it is ought to away. So, standard deviations would give me how many, what quantum of distance it is based on the standard deviation multiple. Consider that I write the equation as R p is greater than R L plus k sigma p. This k is the constant value which I can change. Sigma p is given from the data fixed, R L given from the information fixed, R p bar given from the data fixed. So, I want to find out, depending on the alpha value, what is k, and I want to find out that depending on the k value, whether this equation is met. Now, if you see this equation, it is a straight line equation like y is equal to m x plus c, but here inequality sign being there greater than. You change this fixed value of return R L. So, keeping R, what is the fact? That either you can keep changing alpha, which will have an effect on k, or you can keep changing R L. Now, the problem in the sense, as the formulation was given, you want to maximize R L subject to the conditions, that is less than equal to alpha, alpha is fixed. So, you cannot do anything with alpha, you need to concentrate on R L only. So, that is what is written in the second bullet point, change the fixed rate of R L which you want to have and keep finding the straight lines accordingly. Because if you keep changing R L, R p bar is given from the data, k is given from the data, sigma is given from the data. And why I mentioned a straight line, this will become clear to you. If I consider the straight line, we all know equation is m x, y is equal to m x plus c. What is y? The independent variable. What is x? The dependent variable based on which you want to find out y. What is m? M is the slope per rate increase of y as x changes or it decreases, depending on m is positive or negative, and c is the intercept where the line cuts the y axis. So, if I draw it, this is y, this is x, the line is this. So, y is equal to m x plus c. So, this is c. Now, if I consider similarity and in the same way this equation R p bar greater than R L plus k sigma p. So, this is R p bar, I am writing the equation again in red color for better differentiation. Now, it becomes very obvious the value of c is akin into this equation is RL. The value of K is almost equal to the concept of M, and RP and sigma p are the concepts which we can utilize, considering RP bar is Y, sigma p is the standard deviation. You can consider in the other way round also, like sigma p as Y and R bar p as X. So, we can change the equation. If I consider this equation as given, the line looks like this. So, if you remember in the equation I said RP bar was Y, sigma p was X, I have drawn it exactly as this for simplicity for understanding. And the equation was, I will write in black, it was RP bar greater than equal to, I will not write RL now, is K into sigma p. Why I have not written RL? Because I wanted to use a different color, because it is changing, it can be changed. So, it is RL. So, consider, no, let me use the blue color, because as it is in the graph. So, I keep changing RL. So, the first case 1, I take it as RL suffix 1, and based on this the equation is given where I circulate RL1. When I change to RL2, the equation is the second one. Change it to RL3, this the equation is the third one. Change it to RL4, the fourth one, and if you see, only the intercept is changing. The M value, which is the tangent, here in this case is K, which is given as 0.5, is fixed. So, all these lines are parallel to each other. So, RL1 where it intercepts RL2, where it intercepts RL3, where it intercepts RL4, where it intercepts, all these lines which I am denoting by 1, 2, 3, 4 are all parallel. And which point do you consider? The curve which is the best decision which you have of the, if you consider the concept of risk and return for a portfolio, or you consider the marginal utility case, those 3 cases, increasing at an increasing rate, increasing at a constant rate, increasing at a decreasing rate. So, as I mentioned, human beings are always risk averse. The moment one of these lines is just tangent, that is the best point, which I have denoted by P star, and this red arrow means it is moving in the top left corner and goes increasing. The moment it touches its tangent to that curve, because the green curve is fixed, only the blues are changing and you are able to find out. So, conceptually the diagram is like this. Now, coming back to the criteria is maximization of RP bar, which was the third safety first principle, and again the same concepts of the constraints which was there in the second safety first principle is being replicated here also, but in the second criteria it was maximization of RL, in the third criteria is maximization of RP bar. So, if I consider the constraint, I will just mark where alpha is predetermined depending on the investor's decision maker's own constraint sets of safety concepts, and the idea when converted is like this, which is maximizing RP, and obviously this is probability, but again it can be converted into the concept, if I remember, the straight line y is equal to mx plus c. So, this is RP bar is greater than RL plus Z sigma p, but now here very interestingly in the second principle it was maximizing of RL. So, only the intercepts were changing. So, it was parallel lines. Now, it is a different idea. Now, what we need to do is RL is fixed. So, this is, if I again consider the same diagram, type of diagram, sigma p on the x axis, RP bar on the y axis, RL is fixed, which is this point, which I will denote by blue, and the green curves remains, which is the best frontier. Now, what we do is that I want to maximize RL. So, if I consider I want to maximize RP, so I counterclockwise turn the graph, which is shown by the red line. And this value of theta increases. So, I will use theta 1, then it increases to theta 2, is increasing, theta 3. So, these are the angles which I have considered. This is theta 1, this portion is theta 2, and so on and so forth. The moment that line is tangent, which is P star here, so that will give me the best value of trying to basically maximize RP bar set to the conditions that you have. Again I am writing the condition in violet color, which is probability is RP is greater than equal to RL, which when with some alpha value, which when converted becomes RP greater than equal to RL plus some K sigma. K and Z are the same depending on standard normal deviate which you have. So, in the first principle, what we considered is we had two ideas of trying to maximize for minimize the probability, maximize on the right hand side. Second principle was maximizing the concept of RL. Third principle was maximizing the concept of RP bar. And here remember the decisions are A, B, C, D accordingly, and we will basically take RP bar sigma p for those corresponding decisions only. With this I will end this lecture and continue discussing furthermore about stochastic dominance and the concepts accordingly. Thank you very much. Have a nice day.